AP. Section 1.3 is on evaluating limits analytically. Last section we looked at how to do those graphically and numerically. Analytically means basically using algebra. Learning targets, number 1, I can evaluate a limit using properties of limits. Number 2, I can develop and use a strategy for finding limits. Number 3, I can evaluate a limit using the dividing out technique. 4, I can evaluate a limit using the rationalizing technique. And 5, I can evaluate a limit using the squeeze theorem. And so you can see there's a lot going on in this section. We're going to need to look at some properties. Basically, 2 is very general, but developing and using a strategy for finding it. So number 2 is kind of broken down into 3 parts. You need to know what dividing out technique means and the rationalizing technique, and also squeeze theorem. First topic, if f of x, if a function is continuous at some point, as the limit of f of x approaches that number, then the limit can be found by direct substitution. So basically, meaning this, if you have some kind of function and it is a continuous graph, there's no hole, there's no asymptote, then the limit of f of x as it approaches that number is going to exist. And so because of that, you can basically take the value, like x approaches 4, for example, and you can put that number directly into x, into the problem, use PEMDAS, whatever it takes to find the answer. That's called direct substitution. Some basic properties. These are the properties for limits, and that will help you to answer some of the easier questions. And so these are important, and you need to start memorizing. The limit of b as x approaches c. The limit of a number, the limit of a constant is a constant. That's what it's saying. So limit of b as x approaches some value is going to be the same as the problem. Okay, so very quickly, let me do this. We're going to take a look at it from a graphic perspective, so that way I can make sure you understand what this is saying. So I used the same property limit, and I used an example. The limit of 1 as x approaches 5. Please recall from the last unit that this part beside the limit notation is actually, if you're doing this graphically, it's actually the equation y equals 1. And we know how to graph y equals 1. We go to the 1 on the y-axis and we draw a line through it. And so basically, it is this picture. Okay? So graphically, we can see what's going on. And now the question says, what is the height of this graph as x approaches 5? Well, if I look at it from this perspective, here's 1, 2, 3, 4, 5. At 5, I can see this graph has a height of 1. In fact, no matter what value I choose for x, the y values are always 1. And so the limit of a constant is a constant. It's going to be the same as this number. Second property, the limit of x as x approaches c will be c. The limit of x as x approaches c will be c. Okay, here's a quick example. I'll use the same graph. Let's say you had the limit of x as x approaches 3. Again, graphically speaking, you're going to think of this as y is equal to x. Well, y equals x has an intercept of 0 and a slope of 1. And so we're basically looking at the diagonal line. Okay, so we're looking at this. Okay, based on that picture, find the limit of this graph as x approaches 3. So we're going to get closer and closer to 3 on both sides. When I come in from the left, the y's are definitely increasing. When I come in from the right, the y's are actually decreasing, but they're all going towards this, and that will be the answer. Okay, and so the y value there is 3. So the limit of x as x approaches 3 is 3. Notice the notation. Property 3. The limit of x to the nth power is equal to c to the nth power. I have that kind of scooted in the wrong way. Sorry about that. There we go. So the limit of x to the nth is equal, as x approaches c, is equal to c to the nth. So let's see what happens here. Okay, we're going to look at this example to explain this concept. Again, the limit of x to some power as x approaches c is going to be the same answer as c to the nth power. The limit of x to the third as x approaches 2. Well, looking at it graphically, you're going to do the same thing. I'm going to look at it as y equals x to the third, so I can see a visual here. We know from algebra 2 what that y to the x to the third function looks like. There we go, rough sketch. And then our goal is to figure out what the height of the curve is as x approaches 2. And when we look at it from that perspective, my graph is not the best, but it will be that value, 2, according to the notation, raised to the same power, and that's going to be 3. And so 2 is the third, and so that would be 8. So basically, my graph as x approaches 2 is going to reach a height of 8 for x to the third. And hopefully those graphs helped explain the basic properties for limits. Next, we're going to look at direct substitution. We're going to use direct substitution for any function, a polynomial function, which means like x to the second, x to the third, so on, a rational. As long as the answer is defined and it's a real number, we are allowed to directly substitute the value in. We also can use direct substitution for trig functions as well. So what I basically mean for direct substitution is, again, you're going to take whatever the value is, x is approaching, okay, they'll give you some kind of number, you're going to take that number and you're going to substitute it in place of x into your problem and work it out. That should give you the limit answer. But notice the highlighted part. Direct substitution works really well with polynomials and rational and trig functions. Sometimes direct substitution doesn't work nicely up front, and so then you have to learn other techniques using like algebra to figure out how to get it so that substitution does work. Alright, so let's start with number 1. We're looking at the limit of 3x squared minus 1 as x approaches 4. Yes, I could write y equals 3x squared minus 1. I could go to a graph and I could look at it graphically. Yes, I could go to a table and I could look at numbers less than 4 and bigger than 4 and then substitute in and see what all those numbers are kind of hovering around, what they're very close to. But the direct substitution method works really, really nice. And so what I want you to see is that because f of x, this is your f of x, is, let me backtrack, it's continuous at the point as the limit approaches that number. So it's important to remember that. At 3x squared minus 1, we know that's a parabola. Okay, we know it has a steepness of 3 and it's shifted down 1. And a parabola doesn't have a hole. So 4, if I substitute 4 in, it's going to give me a solution. There's going to be an answer for it, meaning that it's not undefined. It's definitely going to be defined at that point. That's why we're allowed to use direct substitution. Alright, so saying that, I wanted to make sure you understood why we were allowed. You're going to just take 3 and multiply it by 4 squared. and then subtract 1. And it's as simple as that. You'll have the answer just by using PEMDAS. And so this is going to be 3 times 16 minus 1. And that's going to be 48 minus 1, which is 47. So now looking at that number, I'm glad I didn't graph that one because I would have to actually go up 47 spaces on the y-axis to find the height of that curve. Number 2, find the limit of x squared plus x plus 2 divided by x plus 1 as x approaches negative 2. Alright, so again, you can use direct substitution as long as, here's your first check, you've got to make sure that this function that they give you is continuous at negative 2. In other words, if I put negative 2 in here, will I be able to get an answer? I'm going to have a negative 1 on the bottom. Negative 2 plus 1 is negative 1. I could square negative 2 and add negative 2 and add 2. So I'm seeing no hole here right off the top, and I'm not seeing a asymptote. And so what I'm going to do is just do a quick, I see an asymptote, but not one that's at negative 2. I should verify that. I see one, but it's not at negative 2. And so I am allowed to substitute. And you're going to put negative 2 in place of x. Alright, so the numerator, I see negative 2 squared is 4 minus 2 plus 2. Denominator is just negative 1 down the bottom. And it looks like 4 minus 2 is 2, 2 plus 2 is 4. I'm left with 4 over negative 1. And so the limit of that problem is negative 4. Alright, moving on. Number 3. 3 is the limit of a cube root of 2x squared minus 42, and we're trying to find it as x approaches 5. And so we're going to substitute in and see if we can find a defined answer. Alright, let's see here. 5 squared is 25, so we're looking at 2 times 25 minus 42, and all of that's underneath the radical. I need to simplify my right hand, so it's still cube root of, and I got 50 minus 42. 50 minus 42 is 8, and I'm looking for the cube root of 8, and the cube root of 8 is just 2. And so the limit of this function is 2. Alright, so far everything's working nicely. Direct substitutions get me an answer, and I don't have to graph and show a table. So that's why this method is a good one to use when you can. Look at number 4. Likewise, same deal. I see sine squared, remember from pre-cal, that we can write it like this instead. Okay, these both mean the same thing. And now I'm going to substitute and put like 0 here. And so I'm going to go to kind of think of the unit circle, go to your sine 0, substitute that in. You can actually just type it in your calculator as well. But the sine of 0 is the y value, and so 0 squared is just 0. There we go. And then the last one, let me do that. Find the limit of 3 sine x as x approaches pi. Then you would show work by direct substitution, and just again making sure that you understand that continuous statement from the last slide is very important. If f of x is continuous at some point as the limit of f of x approaches that number, then you can use direct substitution. And so sine x, we know what the graph looks like from the last unit. It has an amplitude of 3. That graph is definitely continuous, no matter where I am on the x-axis. So because of that fact, that is the reason I'm allowed to do this step. 3 times sine of pi. And now we go to our unit circle in our head. I'm going to drop my 3 down. Now I'm looking for the sine of 180 degrees or the sine of pi. The y-coordinate at pi is a 0. And so 3 times 0 gives me 0 back. Okay, so those first 5 examples, again, are showing you that like it works for trig, it works for rational, and it works for polynomials. Next, finding limits analytically. Well, because direct substitution is an efficient way, it's a really good way to find limits, we want to use it as often as we can. So when a function doesn't work like this originally, sometimes they'll give us problems that aren't as easy as my first 5 examples, then your job is to try to rewrite it in a different form. And if you can do that using algebra, then you very well may be able to find the answer using this easy method. Because direct substitution is an efficient way in finding limits, we want to use it as often as we can. So if I give you a problem that when you substitute doesn't really work, you might want to try algebra skills to rewrite it in a different form so it does. Sometimes what happens when you substitute is you get something like this, 0 divided by 0. We know in our entire math career you can't divide by 0. That's undefined. So if you do get 0 over 0 when using direct substitution, it's actually in calculus called an indeterminate form. Indeterminate form. It means that I cannot determine the limit from that form. Indeterminate form. I need you, if that happens, to try to write the problem a different way. You can use one of the 2 methods from your learning targets. You can use what's called cancellation or dividing out method, or you could use the rationalization method. When you get an indeterminate form and you know that direct substitution doesn't work nicely for you, I need you to try to write the problem differently using either dividing out technique or rationalization technique. Example 1. The limit of this as x approaches 6 is what? Well, first thought might be, let's just try to substitute 6 in there. 6 squared minus 3 times 6 minus 18. Let's see, 6 squared is 36. Minus 3 times 6 is 18. Kind of moving ahead here a little bit. But I really make sure you write all your steps down. And the denominator is going to be 6 minus 6. And on top I see 36 minus 18 is 18. 18 minus 18 is 0. 6 minus 6 is 0. And right there is a big red flag. This is not acceptable. It's an indeterminate form. Back up here. So because of that, that now means that I scratched that idea. It didn't work for me. And that's okay. Sometimes we have to make mistakes to get it right. So since that didn't work, we're going to try one of these methods. The dividing out method is basically using algebra skills to simplify. So next, since I can't do direct substitution, every step you show, and I need to make sure I say this to you carefully, you need to show notation. The AP College Board and the scores of the AP exam, those people are told to be very picky on notation. You need to make sure that you keep writing it down in every single step until you're ready to answer the question. I didn't do it here because I was directly substituting it in and I was able to find an answer that way. Excuse me. But on this slide, when I directly substituted it, it didn't work, so I'm starting from scratch. I'm rewriting the numerator. We can see it's a trinomial, so I'm going to try to factor it. Denominator stays the same. Numerator on top here. becomes x times x is x squared, and 3 times 6 is 18. Those are my factors that's going to allow me to get a 3 in the middle. My sign at the end is a negative. That means my signs are different. I need the sign in the middle to be, well, I need the term to be negative 3, so I'm going to use like a negative 6 and a positive 3. Okay, now what you should be able to see is that my binomial on the bottom is actually dividing out or canceling. And so I'm not ready to answer it yet. I'm going to drop my notation down, show this. Drop down what this is simplified to, which is x plus 3. And now I'm ready to substitute 6 in. So the next step, I can just say 6 plus 3. And then answer the question, which will be 9. Okay, so again, just making sure you heard me, please make sure you write this every single step until you are ready to substitute, and then you can leave it off. Alright, number 2. Find the limit as x approaches 1 of this. This is the same problem I used in the last section when we were graphing it, so we kind of know what's going to happen here. But again, your notation needs to be written down. And then if I did substitute 1 in here, I'd get 0 on the bottom. Same deal on top. It's an indeterminate form, so that means I have some work to do. The numerator is a difference of cubes problem, doc problem. I'm going to take the cube root of the first and the cube root of the second. And then remember from the last section, same problem. We just square the first, change the sign, multiply together, always a plus sign, and square the last. And now you can see this is factored. This cancels for me nicely. And so now I'm left with, I'm going to come up here, I'm left with the limit as x approaches 1 of x to the second plus x plus 1. And now that's simplified. Okay, I'm not going to get an indeterminate form here because there's no division symbol in the problem, and so all I have to do now is substitution. Now that I'm ready to substitute, I do not have to write the limit notation down. I just go ahead and go directly to the problem and substitute 1 in x's place. And so 1 squared is 1, 1 plus 1 plus 1 is 3. So the answer to that question is 3. Okay, question 3, sorry. I have a limit of a rational function. It has a square root. I'm asked to evaluate, to find it by approaching 0. But if I put 0 in for x right now, I'm going to get 0 on the bottom. And so that is going to be a problem. The numerator is not factorable. It is a square root. And so this problem, I will have to use what's called the rationalization technique. You're used to it when we did like conjugates of imaginary numbers, dividing complex numbers, radicals, things like that. The difference here though is this radical is not on the bottom, so this might look a little strange to you, but in order for me to get this problem in a different algebra form so I am able to substitute 0 in, I'm going to have to rationalize from the top. And so it's going to look like this. Okay, and so now we're going to drop our notation down because we are nowhere near ready to answer this question. We're going to do some algebra work. This is a binomial. Notice this is one term here, this is one term separated by your minus sign. And you are going to FOIL on top, it looks like. So you're going to take this times this, and that's your outside, your inside, and your last. And here we go. On the top, numerator, square root of x plus 1 times itself is just the radicand back, so x plus 1. Outside, the square root of x plus 1 times 1 is 1 square root of x plus 1. Inside, negative 1 times this is negative version of that. And last, negative 1 times positive 1 is negative 1. Notice in the denominator you have just one term here, so you're going to just basically distribute multiplying x times this. Now because this is not underneath the radical, just reminding you from algebra, you can just do x times 1 and call it x and then drop your radical down. And then x times 1 is x. Okay, numerator, I see 1 and a negative 1 here. These are the same radicands. 1 minus 1 is 0, and they cancel. I also see 1 minus 1, they cancel. So basically, not ready to answer it yet, so I drop my notation down. The limit as x approaches 0 of the top is just going to give you an x. And the bottom is giving you x times the square root of x plus 1 plus x. Okay? Alright, so that's what we're looking at right now. I want you to notice that, let's see, if I did put 0 here, it's still going to give me 0 on the bottom. Alright, so might have been smarter of me not to distribute up here. So I'm going to backtrack. And you'll see in a second why I actually chose to do this. So I chose a minute ago to go ahead and distribute it right here. If I would have just left it alone, sometimes it's better if we do that. You'll be able to see what cancels. Way better. Okay, so all I did is copy this stuff back down. Alright, now you can see the x divided by x is gone. Notation comes down. X approaches n. And you are left with a 1 on top and a square root of x plus 1 plus 1. And then you're going to substitute. It's supposed to be 0, wasn't it? There we go. Alright, we're ready to substitute. There should not be an equal sign there. That is my mistake. So now we are ready to substitute. Now we can draw equal if we want. 1 over square root of, put 0 directly into x's place. Numerator stays the same, of course. The denominator becomes the square root of 1. The square root of 1 is just 1, and 1 plus 1 is 2. And we finally got an answer that's not an indeterminate form. Okay, so that's the idea behind that. Okay, next, using trig identities in limits. Trig identities. So when you get like a problem like this, of this nature, you definitely probably want to avoid trying to graph tangent over sine. We did them individually, we just didn't do them as a composition graph. And so I think with this, I would just first substitute, like try tangent of 0. That's like tangent of 0 degrees. that would be 0. So 0 on top. Sine of 0 is also 0, so that's an indeterminate form. So then the next thing, let me just move it over here, you would need to do is you would need to translate this or transform this into using a trig identity. So we know from pre-calc that tangent is the same thing as sine divided by cosine. I'm going to make this a little faster, okay? And then the bottom is just sine x. Well, if that's the case, we know how to convert. Sine divided by cosine divided by sine is the same as sine over cosine times 1 over sine. And you can work all that out. I know you know how to do that. Okay, so sine over cosine times 1 over sine. The sines are going to cancel. I'm going to be left with 1 over cosine x is what I'm going to be left with. And then I'm ready to substitute, so we're going to put equal. Don't have to write our notation. Copy 1 down, copy cosine down, and the cosine of 0. At 0 degrees, what's the x value on a unit circle? Well, it's just 1, and so that means the whole answer is 1. That's how you use identity in limit. And there's other examples I could have given you, but I just chose this one. Tangent converts to sine over cosine, and then use algebra skills to make it simplified. Alright, now I'll put a big red box around this, meaning this is super important. It's Theorem 1.9 in your textbook. It's called Special Trig Limits. These are 2 that you must memorize. Honestly, that is the best thing to do in this situation. This is another concept that they like to ask on the AP exam. So just memorize these. The limit as x approaches 0 of sine x divided by x, if it looks exactly like this, then the answer is 1. Now, if they change it in any way, it doesn't mean it's 1. But if it's exactly like this, 1. Find the limit as x approaches 0 of 1 minus cosine x over x equals 0. Well, when I have this, and I'm substituting 0 in, the answer is going to be 0. And you don't necessarily have to go through all the steps with rationalizing and all that good stuff, or simplifying using algebra. Again, these 2 you just must memorize. Please remember that. Alright, and the last concept is called the squeeze theorem. F of x, notice in my picture, is purple, h of x is red, and g of x is green. The way I have my notation, it's less than or equal to. That means f of x is in between h and g. Noticing that this is less than here, f of x is less than g of x. That must mean g of x is bigger. That's why my green graph is above my purple graph. That's a good thing to notice. The h function is the smallest of the 3. If I had to order these, that's why it is below the other 2. If h of x is less than or equal to f of x is less than or equal to g of x, or in other words, f is between h and g in this graph, for all x in an open interval containing c, open interval like that, except possibly at c itself, and if the limit of h of x as x approaches c is some answer, the book called it L, just to be generic, and that is the same answer as the limit of g of x. If the limit of this red graph as x approaches c is L, and then we find out that the limit of g of x as x approaches the same value is also L, then that must mean the graph between the other 2 as x approaches the same value does exist, and it's L also. Okay, and that's the squeeze theorem. I have basically squeezed in between 2 functions another one, and if I'm asking you a question about, let's say, the limit here, then the answer to the green one is going to be that location. The answer to the red one is going to be that location, which basically means the purple is going to have the same answer.